In this video, we're going to reorientate you to what a parametric function is. We won't do any calculus today, but we want to get you familiar with how parametric functions work and how you can obtain graphs like this one right here, which is not a function of x and y because it would fail the vertical line test, but it is a function if you define your pieces x and y parametrically. So, a parametrically defined function is a function with its variables defined in terms of a parameter. In BC Calc, this parameter is usually t, so x and y will both be defined in terms of t instead of being dependent on each other. So what that means is we're going to draw some curves whose x and y coordinates are determined by a third variable, which we call a parameter. And in general, that's t. It doesn't have to be t, and you shouldn't think of that as time necessarily. So we can have negative time values and things like that. There will be situations where t will stand for time, but not here. So here's an example of a curve c of t that's defined parametrically. Its x-coordinate is a function of t, and so is its y-coordinate. And let's say that those functions happen to be t minus 2 and t minus 2 squared. Just to get a feel for how this works, let's just make a table of values here. So I'll just start t at negative 2. You don't have to start it there. Start anywhere you like. As far as we're concerned, the domain of this guy is all real numbers. But just to get a feel for how coordinates are generated, and then we'll take a look at our calculators and see how to graph these and all those things. So if t is negative 2, we get our x-coordinate by taking the t value and subtracting 2. So I'll go ahead and fill in all these t values. Subtract 2, subtract 2, subtract 2, subtract 2, that would be a 1. Okay, subtract 2, subtract 2. Now our y values are generated by subtracting 2 from our t and then squaring. So I can take this x value, which was already found by subtracting 2, and square this. Here you're going to see some familiar values pop out. But now if we combine these two things together to get the xy coordinates of our points on our graph, you're going to recognize these ordered pairs real fast here. Negative 4 is 16, negative 3, 9, negative 2, 4, etc. Okay, and you're going to say, hey, I know that curve. Okay, so let's just keep in mind I used a domain here of negative 2 to 5. There wasn't anything special about that, but I chose to start my x values, my t values there, and let my t value end at 5. Let's go ahead and jump onto the calculator, because there's some things to talk about here with parametric functions in the calculator. Now, in the graphing screen, you have the normal function mode. If you go to Menu and go to Graph Type, you can select Parametric, which now asks you for two functions, one for x, one for y, in terms of a variable t. Okay, and so we have t minus 2 for our x and t minus 2 squared for our y. And the domain I chose back on the sketch pad was, I believe, negative 2 to 4. There was nothing magical about that. So you could put anything you want in there, but this only graphs the points that are generated when t is between negative 2 and 4. Okay, and I'll go ahead and graph that. And you can see, okay, that's the parabola y equals x squared. At least part of it anyway. Let me change the window a little bit here. I need to go, I think, a little bit higher. So let's go up to 20. Okay, and it only graphs a portion of it because my t values were restricted. And let me go ahead and make a picture of this. What's a little bit different with parametric curves is that we like to indicate the direction that this function was graphed, because unlike normal functions of x and y where we always go left to right plotting our dots, this could have been plotted any number of ways based on the t values. Okay, so in terms of how t was plotted, negative 1, 0, 1, 2, 3, 4, 5, how is this plotted? And in this case, t value of negative 2 gave us the ordered pair negative 4, 16, which would be 1, 2, 3, 4, somewhere up here. And t value of negative 1 gave you the ordered pair negative 3, 9. I'm sorry, negative 3, 9 would be about there. And on and on and on we go. So in this case, the curve was drawn, I suppose, how you would expect it to be drawn, which is left to right. And we can indicate that by drawing some little arrow marks that say, okay, as far as t going t increasing, that's where the dots get plotted on the curve, left to right in this case. And we've already seen that picture of that S, so there's a very good chance that this graph could double back and start going back to the left and maybe even loop over itself, etc., etc. That's possible with these types of functions because they don't have to pass the vertical line test when you graph them in the xy plane. They are functions of t, however. Now, if we go back to the calculator real quick, there's just some things I want you to notice that are potentially unfortunate, but they are what they are. If we go to our analyze graph choices, for example, if we choose minimum, okay, it asks you what graph do you want to use, and we can't click on this graph. So we can't do any of the normal things we do in the graphing screen with a parametric function. You can't find the maxes, can't find the mins, can't find the points of intersection, can't find the zeros. It turns out that this calculator software is just drawing a picture here, and it's not doing the things that it does with the graph mode set to be in function mode. So what that's going to mean is you might have to go back to the other mode to analyze a curve with calculus once we get to that point. Okay, now let's take a look at the application here. Here are two different parametric curves. The first one we just dealt with, which is t minus 2 comma t minus 2 squared. We know what that's going to look like. And here's the second curve, 3 halves t minus 4 comma 3 halves t minus 2. Exercise. We're going to do this two different ways. Find the points of intersection of C1 and C2. Okay, and points of intersection, when you say that, that's talking about xy coordinates. Okay, in other words, in the xy plane, where those two graphs intersect. Okay, method 1 says, do this by setting x1 of t, in other words, the x component of the first curve equal to the x component of the second curve. Solve for t, and then do the same thing for the y's. And you're looking for values of t that we can go back and plug in here and see what occurs. Because remember, this will tell you when the two x coordinates are the same for a given t value, and this will tell you when the y coordinates are the same for a given t value. Those might not necessarily be the same t values, and we'll see what that means in a second here. Alright, so let's see what happens here. If we take the two x functions in terms of t and set them equal to each other, we get t minus 2 is equal to 3 halves t minus 4. I'm going to go ahead and multiply everything by 2 to get rid of the fractions here. So I'll have 2t minus 4 is equal to 3t minus 8. Okay, and if I move the negative 2t to, or subtract 2t from both sides and add 8 to both sides, t equals 4. So what does that mean? Okay, it means when t is 4, our x coordinates will be the same. So let's take a look. I should get a 2 on the left. Do I also get a 2 on the right? I'm going to get 12 over 2. 6 minus 4 is 2. Okay, so when t equals 4, x is equal to 2. Now if we take the y components and set them equal to each other, I have t minus 2 squared is equal to 3 halves t minus 2. I'm going to go ahead and expand this side here. T squared minus 4t plus 4 is equal to 3 halves t minus 2. And once again, I'll multiply everything by 2 to get rid of the fractions. 2t squared minus 8t plus 8 equals 3t minus 4. We have a quadratic function, quadratic equation. Let's put everything on one side and see what we can do here. 2t squared minus 11t plus 12 equals 0. Alright, let's try and solve this by factoring if we can. So that would be a 2t there and a t here. And I need some numbers that multiply to be positive 12. They both could be negatives. So I think 4 and a 3 will do it. That'll be negative 12, and there, negative 3 times negative 4 is 12. Negative 3t and negative 18 is a negative 11t. Okay, so good. What does this give us? Okay, it gives us a time value of 4 and a time value of 3 halves. Okay, and when t is 4, which popped up on the x equation over there, what's the y value? Well, when t is 4, the y value is going to be 4. And when t is 3 halves, the y value is going to be, let's see here, 9 fourths minus 2. So that's 9 fourths minus 8 fourths, I think. So y equals 1 fourth. Alright, so what does this mean? Do the curves intersect here? Where's here? Well, let's see here. When t is 4, then the x coordinates are both 2, and when t is 4, the y coordinates are both 4. So it looks like 2 comma 4 is a point of intersection by method 1. Now, is method 1 good enough? We're about to find out, because when t is 3/2, the x-coordinates were not the same. Okay, so maybe there's more to it than just setting the x components equal to the x components and the y components equal to y components. All right, let me shrink that down a little bit. Now, method 2 says eliminate the parameter. Okay, in other words, we're going to try to make each of these curves functions of x, y in terms of x, by getting rid of the t somehow. Okay, now the first one's very nicely set up for you because x is equal to t minus 2 and y is equal to t minus 2 the quantity squared. So this is a very easy substitution to make because it's set up to do that, right? If x is t minus 2 and y is t minus 2 squared, then y is going to be equal to x squared, making a substitution. And that makes sense because that's the curve we saw graphed a second ago. Now, the second guy will require a little bit of effort here, but not too much. X equals 3/2 t minus 4, and y equals 3/2 t minus 2. So we'd like to solve one of those equations for t and plug it into the other one. Okay. Hope you caught me there. That's not a 4, that's a 2. There we go. So let's do it for the first one. Let's add 4 to both sides and multiply by 2/3. Okay. So we're going to get 2/3 times the quantity, x plus 4, is equal to t. So we can now go over to this y equation. Okay. Therefore, y is going to be equal to 3/2 times this t value. Okay. Well, the 3/2 and 2/3 are going to cancel out. And so we get x plus 4 minus 2, also known as x plus 2. We now have two rectangular curves, y equals x squared, y equals x plus 2. And let's find the point of intersection how we are used to, which is to set the y's equal to each other in terms of x and solve. Again, we have quadratic. Let's get them on the same side. X squared equals x squared minus x minus 2 equals 0. And hopefully this factors nicely. X minus 2 times x plus 1 equals 0. This gives us x equals 2 as a solution, and also x equals -1. And if we plug those into our functions, that's going to give us 2 comma 4 is a point of intersection, and -1 comma 1 is a point of intersection. Okay. Now if we go back up and look at our work for method 1, we'll notice that 2 comma 4, right? When t was 4, x was 2, and t was 4, y was 4. That point of intersection was found by method 1. Okay. However, this second one, x equals -1, y equals 1, this was not found by method 1. So there's something to be said here in a second, but first let's check our work by going back to the calculator and verify. Okay, so here you go. Looks like -1, 1 works, and 2, 4 also works. Okay, so we have done the math correctly. There are 2 points of intersection for those two curves. And so I guess what's the deal with method 1 versus method 2? Why did one give us only one of those points of intersection and the other one give us both? And here's the deal here, okay? When you do this, you're finding where are the x-coordinates the same at the same time. Okay, over here it says when t was 4, x was 2 for both curves. Over here we found that when t was 4, y was 4 for both curves, and when t was 3/2, y was 1/4 for both curves. And only one of those points were both the x and the y the same for both curves, and that was when t equals 4. Okay, so t equals 4, t equals 4, the x's and the y's were in the same place at the same time. That's called a collision point in this parametric world. What it means is at the same time both curves were in the same spot with x and y coordinates. So if you can think of the two curves as objects, okay, at that time t equals 4, they would collide because they'd be at the same place at the same time. Here, -1, 1 is not a collision point. In other words, curve 1 is at -1, 1 at a different time than curve 2. And so the graphs that you get plotted are like their paths, where they were in time, in history, not necessarily all at the same time were they at these points. Okay, so that's a good distinction to make here in this world of parametric curves. the graphs may cross, but they may not be there at the same time. Okay, so this one's a point of intersection, but not a collision point. And if you went back and made a table for the second curve, you'll see that it gets plotted a little bit differently than the first curve, so that one time they do hit and the other time they don't hit each other. Okay, one more thing to talk about here, and this is another way to eliminate the parameter. It's also one of our most famous parameterizations. It's if x is cosine t and y is sine t. Okay, and here's the way you eliminate the parameter in this guy. And you need to see this because you're going to have to do this from time to time. And this is actually done a lot, higher mathematics too, because parametric curves play a big role in Calc 3 especially. If I square both sides of this equation, I'm going to get x squared equals cosine squared t. And if I do the same thing here, I'm going to get y squared equals sine squared t. And let's see here. Let me see. Can I do this? Yeah, let me throw this over here. And let's add these equations together and see what we get here. You're going to get x squared plus y squared equals 1. Why is it 1? Because cosine squared of an angle plus sine squared of an angle is always 1 by the Pythagorean identity. And check it out. This is the equation for the unit circle centered at the origin. Okay, and as long as you let t go through a full range of values that would put you around the circle one time, you'll get the whole circle plotted. Let's take a look at that on the calculator so you're convinced. Okay, so once again, I'm going to go to parametric for my mode here. X is cosine t, y is sine of t, and this is 0 to 6.28, which is 2 pi. Okay, and there you go. There's the unit circle, which again is not a function in terms of x and y. It's actually two functions that you have to graph together. But parametrically, we can handle that because these are both functions of t, and when you put them together, they can make a graph like this or like the s that we started with. Okay, so that's about it as far as introduction. We showed you how to graph a parametric curve if it was easy to plot points. We talked about the direction that the curves can be plotted. We talked about points of intersection, how to find them. So if we go back, you'll find points of intersection always by eliminating the parameter. Collision points you can find by setting the components equal to each other. Okay, and then we talked about this famous parameterization, which you might see again. Then try 10.1, numbers 5 and 9. Both additions work. See you soon.